So we concluded chapter 3 in the previous class, and then now we are moving on the chapter 4, the processor. So this is also very important chapter in this course. So actually, when I think it's the first day on the first day of the course at this course. So I may say, I think, yeah, I said that the important topics in this course is instruction set architecture and pipelining and memory hierarchy. So in this chapter 4, we will learn about pipelining and process architecture of RISC-V. So actually, I will briefly review what we've learned in this course. And then in chapter 1, we learned about the performance metrics of computer systems. So that is also very important. So you need to remember the equation to compare the performance of two computer systems. Okay, and then also you need to remember the equation of execution time of processor. Okay, so it's important. Also in the chapter 1, we learned about some various aspects of the semiconductor technologies, because the computer processor is actually a chip. So that means the system design. So semiconductor technology is very critical for the process architecture or computer system architecture. And then chapter 2, we learned about instructions of computer processors. So we learned about the instruction set architecture of RISC-V, and then so this instruction set architecture is interfaces between software and hardware. So I said that instruction set architecture is a kind of a promise, or is a kind of a protocol between software and hardware. So software is also designed based on this instruction set architecture. So actually we write program code using high-level languages. So these instructions are it's very different from these high-level languages actually, but these high-level code written in high-level languages are translated into the assembly instructions, and these assembly instructions are translated into machine instructions, and then these machine instructions are given to computer processor, and then computer processor generate the result based on the definition in each instruction. Okay, so actually in chapter 2, I mentioned that the hardware is just it's a black box, and then this black box receives the certain instruction and then generate the result defined in instruction set architecture manual. Okay, and then in chapter 3, we learned about the arithmetic engines in computer processors. So in the chapter 2, we learned the many different kinds of instructions, such as arithmetic instructions, logical instructions, shift instructions, that's kind of R-type instructions. Also, we learned about the data transfer instructions called the memory instructions. Also, we learned about the branch instructions, like conditional branches or unconditional branches. So these are the different kinds of instructions in RISC-V. So in order to execute these instructions, we need hardware. Okay, so this is the instructions. Instructions are executed by hardware. So in chapter 3, we focused on the hardware of computer arithmetic. So that's why, because actually we frequently use the arithmetic instructions or logical instructions also. So like add, sub, move, and divide. So in order to run these instructions, computer hardware requires arithmetic engines. So these arithmetic engines are frequently called the processing engines. Okay, sometimes P. So I believe everyone knows that recently the artificial intelligence or some machine learnings are very popular in our academic area, also in the industries. So actually these artificial intelligence applications or neural network applications require heavy computations. So it requires those kind of applications require very large amount of data. So these large amount of data is computed by hardware, so processing engines, and then the results are generated, and then these results are stored in the memory devices. So that's a very simple data flow of the computer hardware. So actually, so this hardware is very critical for the performance of these kind of applications like artificial intelligence, neural network applications. Okay, so that's why we need to focus on the hardware architecture of the computer systems. Also, people entering into this process architecture, we learned about the basic structure or basic architecture of processing engines, because these hardware architectures are also required for designing processors. Okay, and then in this chapter 4, we will learn about the hardware architecture of computer processors. So we start from the single cycle processor first, and we will learn about the pipelining processors. Okay, it's a very critical part of this course. So please study hard for this course, this chapter. Okay. So as I mentioned, so we learned about the instructions. I frequently use INST for instructions. So for instructions in chapter 2, and then based on the definition in instruction set architecture manual, the computer hardware receives the instructions and then generate the result. Okay. So in chapter 2, we just focus on this part, instruction and each result. And then we just skip this hardware part because we will learn about the hardware part in this chapter 4. So in the chapter 4, we will learn about this hardware part, hardware architecture of the computer system. So let's leave it at what we learned in the chapter 1. So in chapter 1, we learned about the performance of CPUs. So now to compare the performance of two different CPUs, we first need to measure execution time. Right? So execution time, the equation the equation is instruction count multiplied by CPI multiplied by TC. So actually, these instruction counts are determined by usually software or instruction set architecture. So software means that is the some algorithms or compilers, like compile options, then instruction set architecture. And then remaining parts, CPI and TC, is also critical for the execution time of computer systems. And then these parts are determined by usually hardware. So as a computer engineer or a software developer, so actually the goal of the engineering is to increase performance and reduce cost. Okay, cost includes some electric power and then manufacturing cost and some some other parts. So these are two main goals of our research and then engineering and then research and design, so R&D. So these are very important. And then these two factors are determined by hardware. So that's why we need to focus on the hardware architecture of this processor. So in this chapter 4, we learn about the very simple hardware architecture of RISC-V. It's a simplified version. It's not a real RISC-V process architecture. So we just to support a few instructions, like these instructions only. Also, the process architecture is very simplified, but this basic is very important because our usual our research and our study start from the fundamental basics. Okay, that's why this chapter is very important. Okay, so in this chapter 4, we will the RISC-V processor will support only 2 memory instructions, like load double word and store double word, and then 4 arithmetic or logical instructions such as add, sub, and OR instructions, and 1 conditional branch instruction like BQ. So only these instructions will be supported by the simplified RISC-V processor. Okay, but these instructions include the data transfer instructions, arithmetic instructions such as R-type instruction, and branch instructions. So actually, every representative instruction types are included in this simplified processor architecture. Okay, so as I already explained this diagram, like this figure in chapter 2, and then just to review. So actually, this is the software side view for the computer processor. So just instructions are given to computer processor hardware, and then the result. So I mentioned that the generated result by instructions are changes of state. Okay. So what are states in computer processors or computer systems? So that is actually the data in memory devices or memory components. So which memories? Register files and main memory, right? So in chapter 2, we learned the various instructions, but these instructions just change the which data? Just change the data in register files like add x1, x2, x3, and also change the data in memories like with the store instructions like SD, x1, 0, x2. So, and then some special instructions such as branch instruction change the PC. PC is also kind of special kind of register because its PC just stores the addresses of instructions. Okay, so that is the some special purpose register. Okay, so instructions just change these state, like these data in register file and memory and program counter. That's it. So what type of instructions we learn? So we learned about the arithmetic logic and data transfer instructions and control instructions like this. And if these instructions are given to processors and then states are changed, then changed states are the data in register file and main memory. So, and then as I mentioned, we just learned this part and this part. So only instruction set architecture defines the instructions and their result. Okay, only this part. So from here to here. But this is just a black box. So we don't know how this process works. Actually, but this process architecture is, as I mentioned, this process architecture is very critical for the overall performance of computer systems. So we need to learn how processor works in the computer system. Okay, so in this chapter 4 and chapter 5, we focus on this processor architecture. Okay. Okay, so let's see how instructions are executed. Okay. So I will explain how instructions are executed in computer processor step by step. So actually in the instruction set architecture manual, so I hope some students already read this instructions architecture manual of RISC-V. So only the instruction formats and some structure of instructions and required data like operands and then result of instructions are just defined. Okay, it's like input of instruction is here and then the output is defined. But let's start from the hardware's view. Okay, and then let's focus on how this instruction or single instruction is executed in the computer processor. Computer processor. So that means the hardware of computer systems. Okay, so let's start from the very simple instruction like add instruction. Add x1, x2, x3. Okay, so in chapter 2, I mentioned that the instruction is also data. Okay, so that means that these instructions are also stored in the memory, it's the main memory, and then in order to access so it looks like this. This is the processor. Processor is here, and then memory is here. And then instructions are stored a certain space of main memory, like the text segment, okay? So we first need to give this instruction to processor, okay? The processor need to read instruction from the memory in order to execute some instructions, okay? It's obvious actually, okay? And then I mentioned that the addresses for a certain instruction is called program counter. So what does that mean? So a certain address, like 0, address 10, at address 10, this instruction is stored, okay? So first, in order to read an instruction from memory, we need to set program counter. So first, we need to set PC for a certain instruction. So in this example, the PC value will be 10, okay? So if the PC is set, then this instruction is pointed by this program counter, and then the computer processor can read this instruction from memory, okay, with the PC. So it's also the hardware model of the memory. So address is given to the memory, right? And then the data is out from memory, okay? So if a PC is set, and then this PC is given to this instruction memory, and then our pointed instruction is out from memory, okay? So instruction is read from memory by this PC, okay? And second, if the instruction is read from the memory, this instruction is just a binary data, it's a binary code, right? So it looks like 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, something like that. So this instruction is given to the processor. So computer processor need to figure out which instruction is received, okay? So this process is called instruction decoding, okay? So computer processor need to know which instruction is received, which instruction is given. So based on the instruction format we learned in chapter 2, computer hardware analyzed this binary code and then figure out which instruction is given to this processor. So for example, so this add instructions, this add instruction can be represented with the binary code, and then we already learned that which part is represent the destination register, and then which field represent the source registers, and then OP code, and the functions 3 or function 7. Okay, based on these rules, the computer hardware just decode the instruction. Okay, and then if we see this instruction, how can we explain this instruction? What is the definition of this instruction? Add x1, x2, x3. So definition of this instruction is that the computer processor reads operands from source registers X2 and X3. So first, the computer processor needs to read data from registers, okay? From this one. So data is read, so this operands are read from register file, so it's registers. And then what is required? In chapter 3, we learned about the processing engines. So this is the add instruction. So this instruction requires what hardware? Adder. So this adder receives two operands from register file and generate the result. Okay, so this will be 64-bit adder. So what is required? Processing engines are required. Okay. The results are generated from these processing engines. Okay. So from the hardware. And what is the definition of this instruction? The result is stored in X1 destination register. So the results are generated from the adder, this adder, and then the generated result is transferred to the register file. Okay, and that's it. And then computer processor complete these required operations, the defined operations in instruction set architecture. Then the next instruction will be also executed. So this process is repeated again and again. But in order to execute the next instruction, we need to access the next instruction with the new program counter. Okay, so because the instructions are changed, so PC should be also updated, like 0x1 4. So why this is 4? Because the size of instruction, the size of RISC-V instruction is 4 bytes, so 32 bits. So why do I explain this? Because these operations are required in the computer processors. So these operations should be implemented in computer processor hardware. So when we design a hardware of a computer processor, then the hardware need to support these operations. So these are the required operations. So let me use the different color. So I used some numbers for each operation. So actually I distinguished some required operations. Okay. So in step 1, the instruction is read from the memory pointed by program counter. So this operation is called instruction fetch. Okay. So fetch means that a certain object is read from a certain space, and then this object is transferred, is delivered to me or some other some processing engine or some other people. So that is the definition of a fetch. So instruction fetch means that the instruction is read from the memory, and then this instruction is given to computer processor. So this is called the instruction fetch. And the second step, is actually instruction decoding, decode. So I mentioned the instruction decoding. So actually this operation is called the instruction decode. And then the third of the step 3 is execution. Because the defined operation is executed by a certain hardware, certain processing engine. And then this last step is called the write back. Okay, because the result is written to register file, but it's written back to the register file, because actually the register file is accessed by during instruction decode step. Okay, so in this example, I just mentioned the 4 different steps, but one step is missing. That is a step for so actually in this example, I take an example from the arithmetic instruction, but we need the RISC-V also has data transfer instructions. Okay, so memory instructions like load and store instructions. Okay, so these instructions are different from the normal instruction because the memory instructions access memory, okay, not register file. So what is missing? The memory access is missing. Okay, so if the load or store instruction is executed in a processor, then based on the definition, the memory is accessed by generated memory addresses. Okay, and then data is out from the memory, that is the load, and then data can be stored in the memory, that is the store instruction. Okay, so this process is missing. So this is the another step for the different kind of instruction. So it's called the memory step. Okay. So in this slide, so this slide also explain what I explained for different steps required for executing instructions. Okay, so PC is updated, and then it's a fetch instruction. So that is the instruction fetch, and then so actually the instruction decoding is not explained here, but the register numbers. So actually, based on the instruction decoding, we can know the register numbers for operands, and also there is a source registers, and then also the register numbers for destination. Okay, so this is the instruction decoding step. Also, depending on instruction class, such as arithmetic or data transfer or branch instructions. So we need some processing engines, and then this processing engine is called the ALU. So we will learn about the ALU later. And then the memory can be accessed by load and store instruction. So that is this step, so memory step. And then, so this write back is missing here, but is required also. And then the one execution of a single instruction completes after these steps, and then new instruction should be executed again. So PC should be updated. Okay. Okay. This is very important. So just to start from the what we learned in chapter 2. So in the instruction set architecture, the behavior, that is the input and output of instruction, is defined, and then think like that. So what is required? So in order to execute this certain instruction, think about what steps are required in hardwares. Okay. So based on those requirements, I explain the required steps in computer processors, and then actually the computer processor hardware is designed based on these steps. Okay, that's why these steps are important to understand the computer processor design. Okay. Okay. So let's review what you learned in digital system design. So I believe some students already took the digital system design course, but I found that about 5 or 6 students did not take the digital system design course, digital logic design actually, digital logic design course. So I will briefly review the basic of logic design. So I repeatedly said that the computer processor is the digital system. So computer processor actually handles the digital signals like binary code. So actually this digital signal is represented using voltage level. So if the data is 0, that means that it's the low voltage or ground. And then if the data is 1, and that means that it's the high voltage or VDD, that means the supply voltage to a certain circuit. And then this data is stored in memory, and then this one digit of binary data is called the bit. Okay. Also, we can distinguish the logic to combinational logic and sequential logic. So combinational logic means that it's just a black box like this. It's a combinational logic. And then if input is given, like adder hardware, so input is given, the output is generated. So for example, if we design an adder, what are inputs? So two operands like A, B. So A and B are inputs of this adder hardware, and then outputs are generated, the sum of A and B. So, combinational logic, just if inputs are just given, the outputs are generated, but after some time. So this time is defined as delay of combinational logic. So input is given, then after some time, after some delay, the outputs are generated. So output of this combination logic is just a function of input. Okay, that's the definition of a combinational logic. So what is the state element or sequential logic? So state or sequential logic means that the state of this logic is stored, it's maintained, and then the output, that means that the output of this logic is the function of input and state. That is the definition of sequential logic. So that means that actually the previous state, the previous result are stored in the state of this logic, and then the output is generated from the current input and previous state of this logic. That is the definition of sequential logic. So actually, the digital design is composed of combinational logics and sequential logics. Okay. So I will skip this part. It's just explain about some combinational logic elements, and then this is important. So actually, in chapter 1, I explained that the computer processor works with clock signal. Okay, so what is clock? That is the repeated pulse, and then this repeated pulse has the same period. So why clock is important? Because so usually in a digital logic design, this is the sequential logic, D flip-flop. And then also D flip-flop is here, another D flip-flop is here. And then between these two D flip-flops, there is combinational logic. So what is in the previous slide, I explained that the combination logic is just input is given, then output is generated. So that means that if the input values are changed, the outputs are changed. So we cannot control the flow of data with the combinational logic. So this delay, so I said that the outputs are generated after some delay, but this delay is different by input values and then some conditions like temperatures or processing variants, like some artifact, some errors in the processors, like the processor variation. So actually, these delays are influenced by many factors. So we cannot control when the outputs are generated and then stabilized. Okay. So we assign D flip-flop, and then this D flip-flop is synchronized by clock signal. Okay. And then the output of combinational logic is stored in D flip-flops. Okay. So at the rising edge of the clock, the input of this combinational logic is stabilized. So this input is given to this combinational logic, and then after delta t, it's a delay. The output value of this combinational logic is stabilized. So output is generated. Okay, but we don't know when the output. We briefly know, but the output, this delay can be changed by any factors. So after some delay, these output values are stored at rising edge of the clock by this D flip-flop. So after some time, at the next clock, this output becomes another input of another combination logic, the next step. Okay. So this is how digital logic works. And then actually this is the basic of pipelining. Okay, so you need to understand. So pipelining is like a conveyor belt, but digital logic works like conveyor belt. Okay, so for example, when in a car factory, there are very long conveyor belt, and then different workers do different jobs, but with this conveyor belt, some tasks are done by worker 1, and then after some time, this output is transferred to the another worker 2, and then another task is done by worker 2, and then after some time, like this. So this is the basic of pipelining, and actually the is flip-flops and combinational logic works at a pipelining manner. Okay, so actually the pipelining is a very important concept in digital system design. So actually in the computer system, in this course, computer architecture course, you need to understand how pipelining works. That's very, very important. And then actually digital design works like pipelining, because digital design is composed of this sequential part, D flip-flops, and between two D flip-flops, there is combinational logic. And then the output of combinational logic is sampled by clock signals, the rising edge of clock signals. Okay. So also in the chapter 1, the execution time is defined. Okay, instruction count multiplied by CPI multiplied by clock period. This clock period is here, TC. Okay, so TC also influences the execution time. Okay, that's why clock signal is very critical for the computer processors. So I'll skip here. So that's what I explained. So usually the one step of this test system looks like this. So it's the state element is here, and then here's the another state element, and then between these two state elements, there is combinational logic. So that means the input of combination logic is provided by output of this state elements, like D flip-flop, output of D flip-flop, and output is generated after some delay. But this delay should be shorter than the clock period, right? Because the output of this combinational logic should be sampled by the next clock edge at state element 2 here. Okay. So that's how the digital design or digital system works. And then also the processor is kind of digital systems. So that means the processor also works like this. Okay. So let's start from the required steps of executing instructions. So in a previous slide, I explained about the 5 steps, including memory steps, required for executing instructions. Okay. The first step is the instruction fetch. So IF is an abbreviation form, and the instruction decoding and execution. The memory. Memory is for the load and store instruction, and write back. And then also when I mention these required steps, I also mentioned some hardware components. So what is required for instruction fetch? The memory is required, also the program counter. So I said the program counter is a specialized register. So there is also a hardware component, because the program counter value is stored in this register. Okay. And then when I mentioned the ID, register 5 is required execution, some processing engines, and then this engine is called the ALU. So that means arithmetic and logic unit. Okay, and the memory step also we also require the memory. Then also we require the register 5. So based on the steps I explained, we can connect these hardware components. So this is the PC, and then based on the data in this program counter register, so PC, with this PC, the memory is accessed. Okay, so let us assume that the instruction is stored in the instruction memory. Okay, so this memory has instructions, and then these instructions are accessed by program counter. So if the PC is given to this instruction memory, instruction is out from instruction memory. Okay, then the instructions are decoded, and then based on a certain field of the instruction, the source registers like RS1, RS2, and the RD is given to the registers. This register is called the register file because there are many general purpose registers. So the ALU is here. So ALU receives 2 operands from registers, and then the result are generated by ALU, and then also load instruction and store instruction requires the address generation. Like, so how can RISC-V generate the address value, address values? Okay, so actually, so the load instruction looks like the base address and offset. So actually, this is the x1 plus immediate value. So this is just the adder. So this address generation is performed by ALU because ALU is the arithmetic and logic unit. So arithmetic operations like add, subtract, can be performed by this ALU. Okay, so address is for the data instructions. The address are given to a certain memory, like called the data memory. So data is stored in this memory, and then the result of ALU or the data comes data from data memory can be written back to the register file. Okay, this is the write back. So, and then for the next instruction, we just calculate the program counter for the next instruction, like a PC plus 4. Also, for the branch instruction, like a BQ, the PC is new PC value is the current PC plus immediate value. Okay, so the immediate value multiplied by 2. So computer hardware also requires this operation. So we need the add, and then this add receive the PC, so it's the current PC, and immediate value from instruction. Okay. So this slide shows some basic processor architecture or connections to execute the instructions. Okay, so I repeat it. So in the previous slide, I mentioned the required steps and components, the hardware, and then these are required hardwares, and then based on the required operations, the components are just connected each other with these lines. Okay, and then based on the required steps or required operations, we added some additional hardwares, and then we connected these hardwares. Okay, and that's it. But in a circuit, the design, if some signals are connected like this, so that means that this line represents the data flow. So that means, so in this figure, the PC and instruction memory is connected like this with this arrow line. So this line represents the data flow between PC and instruction memory. Okay, but if the data is just connected like this, so that means that if data is just connected with like this, then these all lines, like this line and this line, have the same value. Okay, that's it's very simple. It looks like it's just like wire, so electric wire. So if the wire is just connected to each other, then these wire have the same voltage level. Okay, right? Okay, so in this case, so we cannot just connect these two wires like this. So we need the MUX. Okay, here. And then if the MUX is included in the circuit, this is the design, then we need control signals. So in this slide, we just define the data flow. We just define the required steps for executing an instruction. And then we define hardware components required for instructions. And then also we define the data flow between components. So we just connect the components, two components with the lines. And then these lines represent the data flow. Okay. But this is not possible because if the two lines are connected, then these lines have the same value. But we know that, so for example here, this value and this value should be different. Okay, because this value is the PC plus 4, and this value is the PC plus immediate multiplied by 2. Should be different. So in order to connect these two different lines, we need the MUX, the multiplexer. And then if we add multiplexers have control signal like cell. Either because multiplexer looks like this. There are two inputs and then one output, and then selected input is selected by selection signal. Okay, so this is the control signals. What does that mean? Some hardware components require control signals. Then for proper operations, we need to also generate control signals. Okay. So actually, in the next class, we will learn how to design single cycle processors. So basic design of the single cycle processor is composed of data path design. So data path means that it's the computer, just the hardware, the required hardware. And then between these required hardware, the data flows between these data components like data path. And then this data flows should be controlled by control signals. So we also need to consider the control signal design in the processor design. So that's why I explain about the hardware, the required hardware components, data flow, and controls. Okay. Yeah. Okay. So I will explain about the data path. So this is the overview of the computer processor. So I will start from the data path and data flows and control signals. So what is the data path? So definition of a data path is the elements that process data and addresses. Okay. Elements that processes data and addresses. So just this data path means the hardware component such as memory, like instruction memory and data memory. Also the register file, because register file also receives the register file number and the data is stored and read from register file. Also ALU received two operands and generate data, does generate output based on the selected operations. Also MUXes. So database means that just to receive a certain data and generate the output. That is the definition of data path. Okay. So that means the required hardware components I define when I explain about the required steps for executing instruction. Okay. So, and I will explain step by step for each step based on these data path and data flow. Okay. Okay. Instruction fetch. As I explained about the instruction fetch in the previous slide, I believe everyone still remember how instruction fetch work. Okay. So first, what is the definition of instruction fetch? It's very simple actually. The fetch instruction on instruction from memory. So we can replace this fetch with read. So read instruction from memory. So that is the definition of instruction fetch. So and then for this instruction fetch step, we need what data path? Which data path is required? So I already explained PC and instruction memory. Okay. And for the next instruction, we need to calculate the PC plus 4 for the next instruction. So actually, so this operation requires the adder. So we also need the adder. So if you see this slide, you can know that PC is here, instruction memory is here, and adder is here. So these PC register, instruction memory, and adder are required data path for instruction fetch. So we start from this PC and instruction memory and add. So for this instruction fetch operation, so let's start from the instruction memory. So instruction is stored in this instruction memory. So what should be given to the instruction memory? It's PC. So what does that mean? PC is an input to instruction memory. Okay. Then what is the output? Output is instruction. It's obvious, okay? It's very simple and it's very easy. So why do I explain like this? The second lab assignment, for the second lab assignment, you will be required to design data path, okay? So when the data path is, how can I say? So when we design data path, the input and output of the data path is defined, and then also the operation that is called the behavior of data path. The behavior of data path is also defined. And then as a hardware engineer, you will be required to design data path based on this definition. Okay, so what I defined input and output, and then also the behavior of data path, and that's it. So instruction memory is a kind of data path. So what is an input? PC. And then this PC will be 64-bit data, okay? Because this is the 64-bit computer. So PC is the 64-bit data, and then this PC is given, the instruction is out from instruction memory. But what instruction? The instruction in the space pointed by this program counter. Do you understand what I said? Okay, so what is the output? Instruction. Then instruction, the size of instruction is 32-bit, so instruction will be 31 down to 0. Okay, so the input port of this instruction memory is the address. The address has the 64-bit, and then instruction is the output of the instruction memory. The size of instruction is the 32-bit. Okay, input and output. Also, I define the behavior. Okay. And then this is the 64-bit register. So this PC has the program counter value. Okay, the PC register. So this is the 64-bit, and then this also be 64-bit. So actually, the PC is synchronized by clock signal. So that means that What is the input of this PC register? Oh, this line. Oh, if you follow this line is the, oh, this line plus, let us assume that this is A plus 4. What is this? This is the current PC plus 4 because this line is just connected to the adder. So this is the PC, so 63 down to 0, and then it's a 4. So this is the next PC. The next PC is the also 64-bit data. So when this next PC is updated, next clock, because we are designing single cycle processor. So single cycle processor means that every instruction completes each operation, each execution within one clock. Okay. So that means if the add instruction is fetched at the rising edge of the clock, and then the execution of this add instruction completes within one clock period. And then at the next rising edge of the clock, next instruction is fetched. Okay. So that's why this PC is synchronized by clock signal, just sampled by clock signal. So for this PC register, what is the input? Input is the next PC. So next PC means that program counter of next instruction. Output is the current PC. Then this current PC value is just connected to the input of instruction memory. Also, this PC is given to the adder. Then this adder generates the PC plus 4. Okay. This is the instruction fetch. So in this instruction fetch step, I explain the first, I define the behavior of instruction fetch step. Then I define the data path, that is the hardware components. When I define the data path, I define the input and output of each data path, each component. And then also I define the behavior of this data path. So you will be required to design this data path with system verilog, okay? Because those operations are defined, okay? It's given. And then these are the data paths, and then we connect input and output ports of data path using wires. Okay. So this wire was this line represent, as I explained, represent the data flow between data path. Okay. Understand? So you need to understand. Okay, this is very important. So, so in the next class, I will also explain about the data path and then some controls of the other steps, the remaining steps like instruction decoding, execution, and memory and write back. Okay, and then I hope we can complete the single cycle processor design before midterm exam. So midterm exam will be included until the single cycle processor design. Okay, so actually this slide, okay, yeah. So I'll stop here. Do you have any questions? Yeah, thank you for your attention. So see you in the next class. Bye, guys.